Welcome, everyone. Today, we're focusing this explainer on unlocking one of the most fundamentally misunderstood concepts in complex algorithms. Look, if you spent any time studying computer science, data structures, or tackling coding interviews, you probably think you have binary search completely figured out, right? You're likely picturing a neat, perfectly ordered list of numbers. But what if I told you its real power actually has absolutely nothing to do with looking through a list? Okay, let's dive into this. Section 1. Beyond the sorted array, a paradigm shift. So, here's a question for you. How do you use binary search without an array at all? I know it sounds completely counterintuitive, right? Like a trick question. We are taught literally from day one that binary search requires a sorted array to function. But actually, this is the exact assumption we're going to challenge and dismantle today, directly from our source material. Because trust me, once you understand how to answer this question, your problem-solving toolkit is going to expand exponentially. Section 2. The Classic Foundation, Standard Mechanics. Now, let's quickly ground ourselves in the basics we already know. In the classic textbook halving process, you establish boundaries by setting your left pointer to 0 and your right pointer to the end of the array. Then you calculate the exact middle and simply check if that middle element is your target. If it isn't, well, you toss out half the search space and repeat. And this brilliantly illustrates the whole O of log n efficiency, which is the baseline logic of elimination that we're about to build on. Section 3. Squashing the biggest bug. Off by 1 errors. Okay, before we get to the really advanced stuff, we need to address a major pain point. The absolute #1 bug developers encounter when implementing a binary search is the dreaded off by 1 error. It is incredibly frustrating. You can understand the theory perfectly, but your code either somehow skips the target entirely or just gets stuck in an endless loop. So, the crucial point is this. To avoid those disastrous infinite loops, you need to use a really precise template condition. Specifically, while left is strictly less than or equal to right. It's that equal sign right there that acts as your safety net. It ensures the loop actually terminates when the search space is truly exhausted. Seriously, burn this template into your memory because you're gonna need it to be absolutely rock solid for what comes next. Section 4. Searching the answer space. Searching solutions. Let's move on and see how this builds up. We need to contrast the classic model with our advanced model. In the classic way of doing things, you have a target and you just want to know where it is in a physical list. But in the advanced model, there is no array. Instead, you're searching through a logical range of potential solutions. You know, an answer space. You are applying that brilliant halving logic not to a physical list of numbers sitting in memory, but to the bounds of potential solutions. Let's ground this abstract theory with a concrete example, shall we? Whenever a problem asks you to find the minimum x such that a specific condition is true, boom, that is your massive clue that you can binary search on x. Take the famous Koko Eating Bananas problem. You aren't given a sorted array of bananas. Instead, you're trying to find the optimal speed at which Koko should eat. So you pick a speed right in the middle, let's say 5 bananas an hour, and test if she can finish in time. If she can, maybe she can eat slower. If she can't, she absolutely must eat faster. You see, you are executing a binary search on the eating speed itself. It's a real game changer. Section 5. Leftmost and rightmost variants. Boundary variants. Now, what's really interesting here is that because you're testing a condition across a range, you often end up with a whole sequence of falses followed by a sequence of trues. Your job is to find the boundary where it flips. The leftmost variant finds the absolute first time the condition becomes true. On the flip side, the rightmost variant finds the last possible time a condition is true right before it turns false. And each of these requires slightly different logic in your code so you don't accidentally step over that boundary line. Section 6, a new problem class, a powerful framework. So what does this all mean? Well, once you start seeing binary search as searching an answer space, an entirely new class of problems completely opens up to you. I mean, once you stop strictly looking for arrays, what other answer spaces can you search? Could it be the minimum capacity of a cargo ship, the maximum distance between 2 points, maybe the optimal threshold for a complex calculation? The possibilities are literally vast. Apply this expanded mental model to your next impossible problem and just watch how quickly you have your way right to the solution. Thanks so much for joining me on this explainer, and hey, happy problem solving.